这做实验的把它利用，但是这个过程，他们自己有，我觉得他自己不会做实验，是干的其他人做实验就是我们，但是他确实有一个实验室，他有一个 lab， 就是他可能他也在自己打的，我知道，我知道。他们学生里面就有个实验室，这么来理解。第二个呢，虽然一样说一样的理论。Well, no, sorry, they do the theory. I don't know if they, no, sorry. Actually, I see. Why open this? I'm like, where do I have this? No. 是通过了一个慢节奏的导材。那为什么会跟甲马去？为什么？我还是看不见了。或者是。后面打了4条。因为他给我我现在这样。我这个哎，这也你说应该是你应该是Yeah, you tell them how it's I will do it now. Yeah. 这是光彩，这是一个单位是的。没有，将不是我调，但是将来我调的。就表演出来调。那个是爵士。Gold copy。无教有那个是不是知道你听着那个是英文的。移动中午中。就是中午是下午到了。我都不知道。但是比如现在搞一些。So, what about the one just scattering between so you only control that and then one that with scattering and that's like a very weak interaction. So it ends up being Bayesian squared because it's n1 squared is 2 squared. Okay, let me get started. So I'm going to pick up today where I left off. My lecture this morning is going to kind of be in 2 parts. One is just going to be the continuation of what I didn't get a chance to finish saying yesterday.
in particular making some kind of more general comments about optical measurements of Berry's phase and topological effects. And then I'm going to kind of shift gears, if you will, and kind of go into something which is kind of between a lecture and a more conventional seminar, and talk about one particular topic that my group has made some important contributions to recently, which is measuring the topological, or one might say quantized, Axiom Magnetoelectric effect in topological insulators. And one of the things you'll see is that the story of that brings together many of the aspects that I talked about in the previous lectures. So what I want to do is, first, as I said, finish off what I talked about yesterday, and that's making some general comments about things like Berry's phase and topology. Now, many of the concepts, as I mentioned, are probably known to people in the room, and Professor Raphael covered many of these things yesterday. The notion of topology, in particular, has been, of course, much in the limelight in recent years because of the interest in topological insulators and states of matter that originated from that. Topological insulators, of course, themselves, so we didn't call them that at the time, but that itself is a kind of an old subject. And the very first topological insulator we had was the quantum Hall systems. And so in quantum Hall effect, one takes a two-dimensional. This guy doesn't seem to work.
There's another one.
We're going to turn it on.
It's a non-button.
On the side. There we go. Great. So in the quantum Hall effect, one takes a two-dimensional electron gas represented here, puts it in a strong magnetic field. If the magnetic field is not so strong, you get we can understand it in semi-classical language of these cyclotron orbits, and they form a cyclotron resonance at finite frequency. And this is what I just discussed yesterday, and showed this very beautiful data where we were able to partition the terahertz light into left and right polarized pulses. But if the magnetic field is large enough, and you measure the resistance, both what we call the longitudinal resistance as well as the Hall resistance, which is the voltage divided by the voltage in the transverse direction divided by the current, you get this kind of very beautiful series of steps. And what was noticed by von Klitzing now almost 40 years ago is that these steps in the Hall resistance are given exactly by this expression here, h over e squared, fundamental constants of nature, divided by 1 over n, where n is an integer. And these things, these plateaus, these so-called quantum Hall plateaus, are as exact to anything that we can measure in condensed matter physics. They're exact to 1 part in 10 to the 10th. And so this presented an issue in the early days of trying to understand how to understand or how to conceive of this problem. There was early advances by things like, say, Bob Laughlin with the Laughlin thought experiment as how this quantizations could be so exact, the so-called Laughlin gauge arguments. But the notion of how to try to conceive of each of these plateaus and how this plateau could be different from that plateau was a mystery in the early days, because we are used in condensed matter physics of trying to distinguish one state of matter from another state of matter by the symmetries they break. And each of these plateaus, this is an exactly quantized value, and that's an exactly quantized value, and they're different exactly quantized values. And so they're not the same exactly quantized values, so the states of matter have to be different in some very fundamental way from each other, yet the symmetries they break were completely the same. And so this was a big mystery as how to understand the difference from this plateau and that plateau, until it was pointed out by Fowlis and collaborators that there are topological aspects to the wave functions. And it was understood by people like Berry that since quantum mechanical wave functions can be regarded as some kind of geometric object in Hilbert space, things like the inner product and the distance between two vectors in the Hilbert space can be defined, then these wave functions themselves can be regarded as geometric objects. And in particular, if we take a quantum Hall system and we put it on a lattice, this is the usual block decomposition of wave functions, and this is the block function right here. And what Fowlis and collaborators showed is that you could write down a form for here the Hall conductivity, sigma xy, where over the two-dimensional Brillouin zone, this quantity here, which if you regard u sub k as these u sub k's as these geometric objects, this thing here, these inner products, and you can say u sub k dkx, u sub k dky, but this is dky dkx. This has a form which is isomorphic to that of the Gaussian curvature for a surface in two-dimensional surface. And integrated over the Brouwen zone, it's an integer, or sorry, it's not an integer, but it's modulo 2 pi. We're dividing by 2 pi right there, and hence e squared over h. This is why another, if you will, alternative explanation for the quantum Hall effect and why the quantized Hall effect is so exact, because, if you will, all filled bands over integrated over Brouwen zone, this quantity here has to be an integer, and what it tells us is that all two-dimensional insulators, if they're gapped, have to have a Hall conductance, which is e squared over h times an integer. So we're going to come back to this in a later part of this talk, but I just want you to tuck that in the back of your head, that what this basically tells you, again, is that all insulators, which are two-dimension, at the level of non-interacting electrons, all insulators in 2 dimensions, which are gapped, have a quantum Hall conductance, which is e squared over h times an integer. Usually that integer is 0, but in interesting systems like quantum Hall systems or Chern insulator systems, that integer can be non-zero. Good. Now, this guy here is called the Chern number, and written in this form is called the TKNN invariant over the 4 gentlemen who wrote it down, and with the T in the front is Thales, who recently won a Nobel Prize for it. Now, it's been understood what has happened in the last few years is a remarkable synthesis of a number of different things, which were kind of understood, but if you will, we were grasping different parts of the elephant and nobody quite could understand what was being seen over the last 50 or 60 years. If you go into Ashcroft and Merman, as Gil said yesterday, and you look down for the semi-classical, you look at the semi-classical equations of motion written there, you see some expressions which are almost written in this fashion. Right? This is just the usual Lorentz force here, which is the time equal to the time rate of change of the wave vector. This is some expression for the group velocity, but what's missing in Ashcroft and Merman is this expression here, which is called, the whole expression altogether is called the anomalous velocity. And you can realize when you kind of look at the, if k dot is something like an acceleration, and this term here looks something like a, k dot is something like a force, this term here is something, in that case, something like a magnetic field. Okay? We call this guy right here the Berry curvature, and one can express the Berry curvature as the curl of a function which is called the Berry connection, and the Berry connection is related in this fashion here to the wave functions, where the wave functions, again, are these guys, and so when you can see the relation of this particular functional forms to these particular functional forms here, but the point is that the gradients of this wave function here operating on this guy is in principle acting on these u sub k's. So u n sub k is the block functions. And so again, the block function is kind of the important object in this. The other part is just some kind of phase factor, which typically comes out of many of these measurements. So this was known, in fact, that this term was known first in the 50s by Luttinger, and is called the anomalous velocity. The grand significance of it was not understood, but now we understand that it's responsible for things like many of the topological effects that we're interested in. It is relevant for things like the so-called the anomalous Hall effect, which is the Hall effect that comes from kind of the intrinsic magnetism of the system, and is, needless to say, a huge area of current inquiry. One of the things, one of the things that's happened, let's say in the last 10 or 15 years, is kind of a larger understanding of, what are all of the basic aspects of, that are really going into what we should consider the textbook theory of non-interacting electrons, and it's remarkable that, one major aspect of it was not really understood, at least the grand significance of it, until the last 15 years. I heard, I was at a conference some weeks ago, and a colleague there was saying that students at this time in, let's say, in the history of condensed matter physics really are kind of living and working in a remarkable time, because you're going to see in your lifetime, meaning your scientific lifetime of your graduate career, basically the complete finish of a particular field. And that's the theory of non-interacting electrons and solids. So, is that good or bad? I think, in a sense, it's good in the sense that, to see a field kind of wrapped up tightly with a bow and with all of this kind of embedded beauty, I think is a very nice thing. Okay, so let's look at some examples of this, and in particular, examples of the kinds of things that we might be able to measure with optics. Now, unlike what I talked about in the first two lectures, there is no general tools that one has to look at Berry's phase effects in solids. So whether that is an intrinsic feature or bug of Berry's phase effects in solids, I don't have any opinion on at this time. Needless to say, these are kind of sometimes very subtle things which are kind of hidden in, again, embedded in various aspects of quantum mechanical wave functions. We have some aspiration to measure things. And I would say the best we can do at this point is, again, trying to kind of grasp at different aspects of the phenomenology in different ways. But there's no kind of general notion of measuring these effects in the same, different from the way that I talked about in the first two lectures, where I was kind of more interested in dynamics of electrons, the energetics of electrons, scattering times, masses. Masses are related to things like self-energies. And there it's kind of clear what we need to do. We're measuring optics at low frequencies. We can parameterize things in terms of self-energies, the effective Drude model, and that kind of thing. We don't have any general theory like that or general tools. Whether that'll change in the future, I'll give you some hints at the kinds of things that are going on now, but whether that changes in the future or not, I don't know. So one particular state of matter that people are very interested in is vial and Dirac semimetals. And in particular for vial semimetals, kind of a textbook case of what one might have is two particular bands, a valence band and conduction band, which are made to energetically overlap, and they do so in such a fashion that they retain their touching points just at two places in the Brouin zone. And with regards to what I was talking about in the previous slide, we can think of the Berry curvature as something kind of like a magnetic field. And in the same sense, these singularities here where the bands touch, these can be considered singularities for the Berry curvature, or essentially magnetic monopoles in momentum space for this quote-unquote fictitious magnetic field, the Berry curvature. What to measure? Well, one of the things that was pointed out early on was that if you look at the inner band transitions of this system, so we look at, say, if I imagine putting the chemical potential right here, and I promote an electron from here to there, the band structure looks very similar to the graphene band structure I talked about yesterday. And recall what I said about the graphene band structure. We could think about those inner band transitions in the context of the Kubo-Greenwood formula. And the Kubo-Greenwood formula had two parts. It had this joint density of states, and it had this matrix element. And there's all this kind of non-universal stuff that comes into both of those. But one of the non-universal stuff that comes into both of those is the effective velocity of these crossing states. And the remarkable thing about two dimensions was that that velocity canceled and gave us a universal conductivity, and hence gave us a universal value for the transmission through a single layer of graphene, right? It was, for graphene, it's 1 minus, the transmission through it is 1 minus pi alpha. Alpha is the fine structure constant. That's a small number. It's 1 over 137.04. And we got some kind of interesting, nice physics. Now, this is a three-dimensional system. So that cancellation doesn't work in exactly the same fashion. There's still a cancellation, but the cancellation is incomplete. And now what I have, instead of a conductance in two dimensions, I have a conductivity. And you can see there's a lot of similarity to this expression to what we had in the expression for the single layer of graphene. E squared over h, our old friend, is appearing there again. N is the number of vial nodes. This expression also works for Dirac semimetals, so it's 2 in the particular case that I've shown you right here. But in all physical systems that we know of so far, the number of vial nodes is more. But then there's this extra term, and you can see that that extra term, omega over Vf, has units of length or inverse length, and because this is inverse ohm centimeters. Okay? So instead of ohms, inverse ohms, which it would be in the case for 2D, omega over Vf, there is this non-universal, there's a frequency dependence, but there's this non-universal value of the Fermi velocity. But let's say we can get this value in some other fashion, perhaps by doing an angle resolved photo emission experiment, and we know the Fermi velocity. This is a plot of the conductivity as a function of frequency for zirconium pentatelluride, which is it's actually a Dirac, believed to be a Dirac semimetal system. And this dashed line is the prediction from this expression with the accepted number of vial nodes and the independently measured Fermi velocity right there. And so you see it matches quite well. What are these sharp peaks down at low frequencies? these are the phonons in the system, right? So zirconium, tellurium-5 has phonons, and so those are appearing, and that's really kind of physics independent of what's going on with the electronic scale physics. Now, this is all again at the linear response. The stuff I'm going to tell you about at the end today is one of the other examples of systems where we can measure something quantized in the context of linear response theory. It's not clear in many other cases what to measure to get at this kind of interesting topological or Berry space physics. Many cases, though, people are starting to be clever and are looking at different kind of, I would say, combinatoric probes where they take different kinds of optical probes and combine them together, or look at systems, let's say, under the illumination of light. So a series of interesting experiments has been done by Ji Shan and Kim-Fai Mak, Penn State, and now at Cornell, on these transition metal dichalcogenide systems, and in particular here, this case of molybdenum sulfur 2, so molybdenum sulfur 2 transistors. Now, this is a material that has this kind of hexagonal structure of molybdenum and sulfur you see laid out in this kind of these triangular layers. But Moly is here, Moly is there, sulfur is there. If you look down from it on top, it looks like a hexagonal lattice, like that of graphene, except there's this kind of zigzaggy pattern in, going up and down in space. If I take a look at the 2D projection of that in the 2D Brillouin zone, I get this hexagonal. This is the real space lattice right here. So that's looking down on top. If I look at the Brillouin zone, I have very similar kind of, at the rough level, very similar physics to that of graphene. In graphene, there are two different kinds of Dirac nodes that sit at what we call the K point and the K prime point. And they're different. They're differentiated from each other by a valley, the different sublattice degeneracy in the system. You have two atoms in the unit cell in graphene. And in the case of graphene, those two atoms, let's say their local on-site energies are the same. But in this particular system, they're different. We can distinguish, let's say, red sites and blue sites. And so what it means is that opens up a gap at what would be the, we go from having, Dirac nodes like that to opening up a gap here. And in these transition metal dichalcogenides, that gap is proportional to the inversion symmetry breaking parameter, the strength of the inversion symmetry breaking potential, and it's something on order of, say, about an electron volt, rather large. Okay? However, the bands are highly non-parabolic, and so in fact, a good low energy description of these bands, I didn't draw it very well, but let me draw it again here to emphasize that point. And so the bands are kind of, if you will, at the K and the K prime points have this kind of hyperbola-esque shape, and if we would make them smaller, the gap here smaller and smaller and smaller, it turns out that one would have at the touching point, and this is the case in graphene, a singularity of Berry's flux. Okay, so in the two-dimensional Brillouin zone in graphene, the K and the K prime points have, if you will, magnetic monopole sitting there, which is a source of Berry's flux. In these two-dimensional materials, as we open up this gap, one way of thinking about it is that I have moved this source of Berry flux out of the two-dimensional plane and into a third direction, which ends up spreading the magnetic field out in space, or in space, excuse me, in momentum space. But what the point is that this kind of portions of the band are regions where the Berry flux is large. Okay? There's a K point and a K prime point. The point is that this kind of fictitious magnetic fields are quite large in this region in space. Okay? There's a K point and a K prime point, and the nature, or let's say the signs of the Berry flux is different in these two different parts of the Brillouin zone. And so if you do a transport experiment on such a system, what do you expect? This Berry's flux is like an internal magnetic field, and so the electrons in the K point feel that fictitious magnetic field, and they go this way, let's say. And the electrons that are in the K prime point, I don't know if it goes this way or that way, I don't remember, but let's just say it goes this way, depends upon doping as well. The electrons in the K prime point are moving along, and they feel the opposite sign of the Berry flux, and they go that way, right? So is there a net Hall voltage? No, right? So you got electrons going this way, curving this way, and electrons going that way. This is all at the level of semi-classics. There's no net Hall voltage, and I do a DC transport experiment, and I see nothing. A very clever experiment was done, though, by these guys at Penn State, where they went and the fact of the matter is that if you go and you illuminate in the two valleys, because of how the particular bands orient themselves, one finds that at the K prime point and at the K point and the K prime point, the relative tendency of electrons in these places in the Brillouin zone to absorb left or right circularly polarized light is different. So they did this very interesting and clever experiment. They took what they called a Moly disulfide transistor. They ran a large current through it. The K electrons go to one side of the sample, right, because they feel a Hall effect in one sense. So the fictitious internal magnetic field, the field pushes them one way. The K prime electrons go the other way. This is, if you will, kind of illustrated here. And then they came in with left hand and right hand circularly polarized light and imaged the relative densities of these. So you run large amounts of current through it. The K electrons end up on one side of the sample, relatively speaking. More K prime electrons end up on the other side of the sample. And then you come in and you image over the sample afterwards, and you find that K prime electrons are on the left-hand side, and K prime electrons are on the left-hand side, and K prime electrons are on the left-hand side. This was actually measured by actually doing a Kerr rotation experiment. So they don't actually come in with left-hand and right-hand light separately. They come in with linearly polarized light, and that linearly polarized light is rotated upon reflection. And so it was a way to image it. It's a very beautiful experiment. It was really kind of a direct optical manifestation of what we would call the valley Hall effect, right? So the K and the K prime electrons feel different Berry curvature. They move in opposite directions. We cannot see this in the usual DC transport, but it's a way of imaging it afterwards. Okay? It's kind of some kind of non-equilibrium, nonlinear probe of this kind of underlying Berry's phase physics. But you can see that it's kind of it's a beautiful demonstration of this physics, but it's kind of particular to the particular case in mind here. We have this clean partitioning of K and K prime valleys. They have particular Berry phase structure associated with them. If you're clever enough, you can come up with some scheme for measuring that, but it's certainly not a general scheme for measuring this kind of thing. Now, there's been another proposal. This experiment hasn't been done yet, but I think it's beautiful enough that I wanted to mention it. And it starts to give us some general idea of how we might start to think about the kinds of probes which might be useful in general. And I don't think we're anywhere close to there yet, but many smart people in the room, so it's giving you something to think about. There was a proposal by these guys in New Journal of Physics in 2013 for what would essentially be a direct probe of the Berry's phase in these transition metal dichalcogenide materials. Okay? So again, that's the Brillouin zone in one of these things, and you can think of, again, of something like Moly disulfide, which has this gap that opens up at the K and the K prime positions. And again, recall that the Berry's phase, we should think of it something like a magnetic field, but it's different at the K prime and the K points. Okay? Now, the proposal was the following. You take a piece of Moly disulfide and let's say gate it. It's a two-dimensional material, so it can be gated by making it into a transistor geometry, and you gate it so that it's essentially electrically neutral. You come in with linearly polarized light. Okay? With linearly polarized light, you can make an excitation from the valence band to the conduction band, right? But recall that the K and the K prime valleys have different tendencies to absorb right and left polarized light. So when I come in with linearly polarized light, what actually happens in such a system? I come in with linearly polarized light. That's represented here by a superposition of, let's say, left-hand light and right-hand light. I make an excitation, and because I've come in with a superposition of left-hand and right-hand being linear, then the particle hole excitation that I make, I need to think of that actually as a superposition of, so it's a superimposed state of making an electron hole pair at the K and the K prime positions. Okay? So after photoexcitation, my state of the system is a superposition of electron hole pair being at K and at, let's say, minus K, which in this case is one of the K prime positions, right? K and minus K is the same as K and K prime. Okay? So this represents the superposition state. Okay, so first a laser comes in, makes with linearly polarized laser, come in and makes this excitation. Then the proposal is that you come in with another pulse, which is a lower frequency terahertz pulse, but high intensity. High intensity that you can take what is essentially this wave packet that's made in terms of the k and k prime positions. And if we imagine we apply an electric field to this system, the electrons are going to respond to what have effectively not, now it's a low frequency pulse, and so we can think of it as a classical electric field. They're going to come in, and we can imagine we're going to come in with a terahertz pulse, which is circularly polarized or elliptically polarized. So what does it do? It takes we make this electron hole pair. At one of the valleys, it then, when we think of it semi-classically, makes the circularly polarized terahertz pulse, comes in at low frequencies, and makes this, let's say, electron and hole undergo this kind of motion in the Brillouin zone, right? And it goes ahead and encircles, let's say, if we think about it locally in k space, encircles the k prime position, which was a place which had a lot of Berry flux. Okay? So what happens when you encircle something which has a magnetic field, a particle, and you come back to where you started? You pick up an Aharonov-Bohm phase or a Berry's phase. So what we imagine then, we come in with excitation, we make a superposition of electron pairs, we come in with a terahertz pulse, this wave function evolves in space and eventually comes back to where it started. So what happens here is it takes some time for this wave function evolution to happen, and there's a dynamic phase that's associated with the k valley and the k prime valley. And the interesting part of this is that that wave function evolution is, in both cases, from the dynamic phase is the same. But recall that the Berry's flux was opposite at the 2 points. And so when this thing undergoes its cyclic evolution, the Berry's phase that these two pieces, the wave function, acquire is actually opposite. And because this piece acquires a different phase than this piece, when the electron hole pair recombines, this phase of the phi b is inherited by the linearly polarized light that forms when this exciton collapses. Linearly polarized light is emitted, and it has its polarization rotated by exactly, I don't have it on the plot here. Well, it's here. Yeah, it's right here. I'm sorry. So what happens, right? We get wave function evolution. This becomes the new wave function after it undergoes a cyclic evolution along the loop. It recombines. The electron hole pair recombines. Linearly polarized light is re-emitted, and the rotation of the linearly polarized light is exactly the Berry's phase that was acquired in the cyclic evolution. So this is, as far as I know, the only really direct measure of Berry's phase in the Brillouin zone in experimental system. I mean, proposed measure. It hasn't actually been done yet. But this would be a beautiful experiment. Okay, so it's a two-step process, a laser followed by a strong terahertz pulse. And this gives us some kind of indication about a way going forward where we might be able to kind of get at some of these effects. And there's been a series of very beautiful papers written by, the first one was this one here, Takahiro Morimoto and Naoto Nagaosa. This paper is from 2016, and Morimoto moved to Berkeley and has written various nice papers with Joel Moore and Joe Orenstein, where they are kind of recasting a lot of what was already known about nonlinear optical effects in solids in terms of Berry's phase, Berry's curvature, and topological effects of solids. And this is already starting to be a rather large field, and I'm not going to talk about it in detail. I just want to mention a few quick things. And again, that's our definitions for the Berry connection. That is this quantity, which is something like a vector potential for these geometric objects of the use of Ks. You can write down things like, let's say, the wave packet position of a block function inside the Brillouin zone, the average position in terms of this Berry connection. And it turns out that you can write quantities, for instance, like the photocurrent. So photocurrent is the current that comes out of a system upon photoexcitation. You can actually write down the photocurrent proportional to the electric field applied squared, but then the constant of proportionality, this is like, if you will, something like the response function of the system, can be recast in terms of these quantities which have to be intrinsically related to the Berry connection. And so this starts to be a rather large and interesting area where people are trying to use nonlinear optics. The field of nonlinear optics is an old one, people using it for technological applications. If you have an 800 nanometer laser and you want to make, meaning 800 nanometer wavelength laser, and you want to frequency double it, you run it through a crystal which has a large second harmonic generation. So a piece of gallium arsenide is a material which will generate 400 nanometer light when you run an 800 nanometer laser into it, wavelengths. Okay? But up until recently, nobody understood anything that you can predict some of these effects just from symmetry. But the magnitude of the effects actually turns out in almost all cases to depend upon these Berry's phase features of wave functions. And this was, let's say, unappreciated until recently, although this expression here actually goes back to 1981, and but I think the grand significance of this wasn't appreciated until recently. This is an expression here for what's called the circular photogalvanic effect. Circular photogalvanic effect is if I take a system and I illuminate with right-hand light, and I look at the time rate of change of the current, and so this is the time rate of change of the current, and I look at the difference from that with left-hand circularly polarized light as I look at the time rate of change of the current under an intensity I. This C here is a number which measures the charge of the Weyl node in momentum space. So this was a proposal of Dewan et al. In 2017, which is a proposal to measure this nonlinear optical effect, which should, if it could be measured, would directly measure the charge of a Weyl node, right? So you want to, we think Weyl physics is an interesting thing, but it has been hard in many experiments to come up with smoking gun signatures of, let's call it Weylness, something which really directly relates to the topological aspects of the wave functions. The singularities of Berry flux. But this right here, if the system has no Weyl nodes, this C function is equal to 0, and this quantity should be equal to 0. So people are working on trying to measure that. Now, there is, again, as with a lot of this field of topological, non-interacting free fermions, theory is far in front of us, poor experimentalists. And the first real efforts, I think, in doing this are coming from Joe Orenstein's group and Darius Torchinsky. Darius is at Temple. Joe Orenstein is in Berkeley. The theoretical support and leadership is really coming from Joel Moore in this regard. And so one of the things they find in this Weyl semi-metal system is this huge enhanced optical nonlinearity where, this is the data is the dots, and this lines are the experimental fits to things that are known about the band, using information which is known about the band structure of tantalum arsenide. This physics, to get the shape of this curve, one is relying on the fact that this is a Weyl semi-metal and has these singularities of Berry flux in the Brouin zone, but that's the nature of these curves. But the data, if you will, at this stage, we still haven't been able to tease something out of the data, which is really, let's say, a smoking gun for interesting physics like quantized Hall plateaus in the resistance. Right? So this is something the community is still struggling with for many of these systems, what to measure, which reveals these kinds of underlying interesting topological or Berry's phase properties in the system.
Question? What's the resonance here?
So this particular resonance is coming, I believe, from so you can see here it's at about 0.7 electron volts, and it's coming from, I believe, the saddle point singular excitations at the saddle point singularity across from one place in the Weyl band structure to another place in the Weyl band structure. So the interesting then to really access and have definitive smoking gun signatures for the Weyl physics, you need to go to even lower energies. But it's hard to do these experiments in a nonlinear fashion. So I was talking about 0.7 electron volts. That's 700 millieV, which is equivalent to about, if we put that into temperature units, that's about 7,000 degrees, right? So that's huge energy scales and the energy scales of solids. Clearly, if you're interested in, the kind of the universal low energy physics, you need to be down in the millieV range, and that's the terahertz range. And those experiments just haven't been possible yet. So I think the community is moving in this direction to be able to do low energy nonlinear experiments, but those haven't been possible yet. So really, when you look at a curve like this, you and I don't see anything that is a smoking gun signature for the Weyl fermions. What you want is to give you a number. You want to measure a number which is with a ratio to some universal E squared over H or some universal constants of nature, which is 1 or -1 or 0. And a fit to a curve like this is messy, but this curve basically comes out of the Weyl band structure. So in this sense, it's a signature of the Weyl band structure, but we're looking for kind of beautiful, interesting, non-universal physics, and that's not in this experiment as has been done so far. Okay. Okay, so let me shift gears a little bit, and I'm going to tell you about one example of something where we do have beautiful universal physics. Before I do that, though, were there any questions about what I've talked about so far this morning about these particular examples of things? No? Okay, good. All right, so let's go on. So here I'm going to shift gears, and what I'm going to tell you about now is kind of an extended version of telling you about some work that my group has been done with. It's going to be in the form of kind of a research seminar talk, but changed in some particular fashion for let's say somewhere between a research seminar talk and a school lecture. So I had mentioned that, of course, the very first topological insulator that we knew about was the quantum Hall system, right? So in a quantum Hall system, 2D electron gas in strong magnetic field, and to make a cartoon version of it, we get a two-dimensional insulating bulk, which is then ringed by these one-dimensional, one-way going edge channels, which have both spin-up and spin-down electrons in them, right? So this is kind of a cartoon version of a nu equals 1 quantum Hall system here. Now, since the early days of quantum Hall, people asked questions like, can we have three-dimensional versions of quantum Hall systems? Can we have quantum Hall systems where we don't need magnetic field? And the answer to these at various points has been yes, but with some caveats. And what has happened in the last few years is now we have a resounding yes to both of these points. And very briefly, to make the point, instead of large magnetic field, which we need for these particular cases, the role of something like large magnetic field is played by spin-orbit coupling. So the spin-orbit coupling, of which a particular form for the spin-orbit coupling parameter can be seen right here. And you can see that in the spin-orbit coupling expression, it comes with it this expression of magnetic field. And so an electron experiencing strong spin-orbit coupling kind of, if you will, brings with it its own fictitious magnetic field wherever it goes. And then it's kind of clear in this regard how you might be able to have a three-dimensional version of the quantum Hall effect. Otherwise, how would you get a 3D version of the quantum Hall effect? The magnetic field's got to point in some direction, and we get these orbits around the magnetic field, so how can I have a three-dimensional version? The only way to have a three-dimensional version of the quantum Hall effect is I would have to somehow stack quantum Hall layers. But it was discovered first by Duncan Haldane in a kind of more rarefied theoretical model that's called the Haldane model. Haldane is here, of course. And then later by a more physically accessible version of this by Charlie Kane and Jean Moly at the University of Pennsylvania, and then another version of this by Andrei Bernavig, who's also here, and Sucheng Zhang at Stanford, that one could get this system to form what we now call the quantum spin Hall system in 2 dimensions, where we can think of it something kind of like a quantum Hall system, but where, if you will, I've taken one of the quantum Hall channels, say one of the spin-up channels, I've taken it off, I've turned it upside down, and I put it back together. So now I have a 2-dimensional bulk, but it's ringed by one-way going edge channels, but spin up goes one way and spin down goes the other way. Okay? Now, then it's clear how I can get a 3-dimensional version of this. A 3D topological insulator is a 3-dimensional bulk, which is then covered on all sides by this 3-dimensional surface states. Now, I don't want to get more into the details of this. There's kind of we can talk all days about the intricacies of the theory of this, but it's found in a gazillion different review articles. I want to give you more kind of an intuitive feeling for how this can happen. One particular construction I like is this particular one. So if we can imagine a conventional insulator, which has a conduction band and a valence band, imagine something like gallium arsenide or silicon or germanium, then there is a certain sense in which I can imagine taking the valence band and the conduction band of this kind of conventional insulating material, adiabatically distorting them into the vacuum states, into the positron, the electron states. The vacuum states of conventional everyday space, it's kind of like a semiconductor, but just with some ridiculously large band gap. So, but there's a certain sense which you could imagine distorting those wave functions from conduction band, valence band in this particular fashion. But that's not the only thing that can happen. One can also imagine a situation where you would kind of undergo this adiabatic distortion of wave functions, and instead of going from here to here and here to here, you get this. If you would do this again at the level of non-interacting electrons and distorting the wave functions, you would find that the conduction band states distort into the positron states of the vacuum, and the valence band states distort into the conduction band states of the vacuum. In order for this to happen, there has to be a level crossing. Well, where does this crossing happen? Well, it makes sense it happens at the surface. We can't get rid of this crossing at the surface unless we do something to unwrap this energetic ordering of bands inside the material here itself. And this is a sense of why we say that the surface states of these materials are topologically protected, because you can't get rid of this crossing unless you do something to change this energetic ordering. The energetic ordering is swapped from the usual situation to this situation here, where this energetic ordering is swapped due to spin-orbit coupling effects. So spin-orbit coupling takes one state and moves it above the other state. Okay? So the gap closes between two different vacua, and this results in this topologically protected surface metal. As another really just cartoon of what is going on in a topological insulator, there's another one that I like. This is what's called the proposed flipper bridge, which is an artist's conception of a bridge going between Hong Kong and mainland China. You know, in mainland China, they drive on the right-hand side of the road like we do. In Hong Kong, they drive on the left-hand side of the road like they do in Britain or Japan. And one cannot, in principle, drive from Hong Kong to mainland China without undergoing a topologically protected crossing. The roads have to cross each other in this fashion here. So this bridge, unfortunately, is beautiful, but it doesn't exist. But the roads have to cross each other, and they have to cross each other an odd number of times. Doesn't matter how many times they do it, as long as it's odd. You can't go from one place to the other without an odd number of crossings. A very, very similar thing is happening in the context of the surface states of topological insulator. Okay, so I talked about the quantum Hall effect, and in particular, the quantized resistances of the quantum Hall effect. The quantum Hall effect is kind of a unique system in the sense that, you know, and it's of course why it was discovered first, is that it's really presents us with some remarkable phenomena that has really held our attention now for going on almost 40 years. These kind of exactly quantized plateaus that come from topological properties of the material. You know, many of us do condensed matter physics because we have some deep fascination with the materials that we're looking at. The phenomena is something that attracts us to the physics of these particular systems, is the phenomena that they present. You know, particle physicists have a very different perspective. You know, they're interested in particles, but particles themselves aren't particularly interesting things. An electron is not a particularly interesting thing. But superconductivity, this is fascinating to everybody who's even understood it very well and worked on it for a long time. People still like superconductors. We still like the quantum Hall effect because these exact quantized plateaus are interesting, cool, remarkable. You can take a dirty system and get out clean universal numbers out of it. So in the context of the topological insulators, you can ask yourself, what can we measure that's like the quantum Hall effect? Can we measure something which is quantized in the same spirit as that of the quantum Hall plateaus in the topological insulators? And the answer appears to be yes. So it was pointed out by Sucheng Zhang and Joel Moore and David Vanderbilt that we can think of topological insulators when we break time reversal symmetry at their surfaces as magnetoelectric materials. So magnetoelectrics are materials known since the 50s. Jalshinsky was the first to point out that there were certain materials that could be magnetoelectrics. These were allowed by symmetry in that case. A magnetoelectric is a material that if I apply an electric field, I get out a magnetization. And if I apply a magnetic field, I get out an electric polarization, right? So it's not the usual state of affairs. Usually I apply an electric field and I get an electrical polarization. But magnetoelectrics, usually like a textbook magnetoelectric, the one that is most often studied is what's called chromium sesquioxide, Cr2O3. The material itself is a beautiful green color, which is also used as pigments in paint, a kind of a green color for paint. But it's also a magnetoelectric, chromium sesquioxide, Cr2O3. If you apply an electric field, you get out a magnetization. If you apply a magnetic field, you get an electric polarization. But a really, 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 really small one, which is set, the coefficient is just some particular number that people have tried for a very, very long time to try to calculate more accurately in the context of ab initio theories. There is this proposal then that topological insulators can be seen as magnetoelectrics. And in what fashion do we mean that? Let's look at a thought experiment. We're going to take a slab of a topological insulator in this fashion. And remember what I had said was that the topological insulators are bulk insulators in the ideal case, but they are wrapped on all sides by this surface metal. Okay? Now, as a thought experiment, I'm going to imagine applying a magnetic field such that this magnetic field is a thought experiment, so the magnetic field is everywhere going to point out. There's some difficulties with getting a magnetic field to point out everywhere. I need magnetic monopoles, but it's my thought experiment, so I'm allowed to do that. And that magnetic field is going to be large enough such that the surface states in this system are going to have a quantum Hall effect in them. The quantum Hall effect is going to be of unusual variety. It's going to have a coefficient which is e squared over h times n, the integer, plus 1/2. And this 1/2 is anomalous, and we're going to come back to that in a minute. But for now, let me just tell you that I have this funny quantum Hall effect on the surface, okay? So I apply an electric field in, let's say, the y direction, pointing up. That is going to give me a quantum Hall effect, which means the current is going to circulate around the slab in this fashion, okay? So I have a surface current kappa, which is circulating around this fashion. A surface current can be written in terms of a bulk magnetization. So bulk magnetization crossed with a surface normal vector is a surface magnetization. And so if I take this expression, I put it together with this expression, I can see that I apply an electric field, I get out in the y direction, I get a magnetization in the y direction, right? Not the usual state of affairs, but with a coefficient which is e squared over h, universal constant of nature, times n plus 1/2. So this is in the sense in which the surface current is equivalent to the bulk magnetization, and we can write everything down as a bulk magnetoelectric polarizability. This is preferable for a number of different reasons. For one thing, it's going to lead to an explanation as to how we can get the 1/2. The other thing is it's preferable to us, when I look at a material like bismuth selenide, which we're doing experiments on, one can conceive in some contexts of bismuth selenide as kind of a bulk material, which is an insulator, but it's wrapped on all sides by this surface metal. This is a little bit of an unsatisfying description of this. It has a description of the material as this kind of inhomogeneous two-part thing. Bismuth selenide insulating in the middle, surface metal on top. But the whole thing is bismuth selenide. The material itself doesn't discriminate about different regions where this particular thing happens or that particular thing happens on the basis of chemistry. It's not a different material on the surface and a different material altogether in the bulk. It's all bismuth selenide. So what we would like would be to have some kind of description of its electrodynamics based on a homogeneous response function of a homogeneous material, which is what it really is. Okay? Now, this magnetoelectric effect can be written in field theory language as an additional term that we can add to the conventional electromagnetic Lagrangian, which has this form here of E dot B. Okay, again, some constants of nature in front, and there is this theta parameter here. This theta parameter is an angle and is going to take on values. In principle, it can be anything, but in materials which have either inversion symmetry or time reversal symmetry, this theta parameter in front has to be an integer times pi. Okay, in a conventional material, that integer is 0. This should sound vaguely familiar to you with what I said about quantum Hall systems. Any gapped two-dimensional material at the level of non-interacting electrons has to have a Hall conductance, which is e squared over h times an integer. Usually that integer is 0. Here, this angle here, theta, can be anything we like if we don't have any symmetries, but we have either inversion symmetry or time reversal. This angle here has to be an integer times pi. And it's going to turn out that it's 0 or 2 pi or 4 pi, even integers in kind of conventional insulators, or it's going to be an odd integer in topological insulators. Okay? And so this work was worked out by all of these various smart people here. Okay, now one other point. The magnetoelectric polarizability is one notices that in this expression here, this e squared over h comes in again. E squared over h, of course, is the quantum Hall conductance. And again, this quantity is coming in here, and it's remarkable to think that it comes in so many different contexts in condensed matter physics. It's the contact resistance, say to a 1D structure. It's the quantum Hall conductance in 2D, and it turns out to be the parameter which also sets the size of the magnetoelectric polarizability in 3D. Okay? These magnetoelectric effects, if they exist, are going to show up in the quantized Faraday and Kerr rotations. So we're going to take low frequency light, we're going to shine it on the sample, and the light is going to be rotated by some amount, and that amount is going to be set by the fine structure constant. We call this form of this kind of magnetoelectric effects, which we can trace back to this E dot B term in the electromagnetic Lagrangian has been referred to as so-called Axiom Electrodynamics. The axions were a particle postulated in 1977 to obtain, an attempt to explain the absence of charge parity violation and the strong interaction between quarks. And Frank Wilczek called them the axion because they so-called cleaned up a problem with CP violation. As Wilczek wrote, I called this particle the axion after the laundry detergent because that was a nice catchy name that sounded like a particle, and because this particular particle solved a problem involving axial currents. So the axion, this is a picture of axion laundry detergent. You can still buy it in South America, I think. It used to be available in the United States, but it's some brand which doesn't exist here anymore. The axion particles as a real fundamental particle still haven't been discovered, but they're a candidate for dark matter, and there are lots of experiments happening in various parts of the world where people are kind of doing these cryogenic searches for cold dark matter, where they're trying to detect. There are not many axion particles around us, and if there are, they're interacting very weakly, but they do try to do these very, very sensitive experiments where they're looking for axion particles. Axion particles still may be kind of a fundamental particle which makes up, some large part of the universe. The original axions of Wilczek, I don't think anybody thinks are a real candidate, but axions kind of are one of these really good ideas that keeps getting recycled. It turns out that the electromagnetic equations of motion, the Maxwell's equations, in the presence of these E dot B term, get modified in such a way which are completely the same as that of what would be the case if we had these axion particles existing in real space. And Maxwell's equations get modified on the surface of a topological insulator. This was also pointed out by Wilczek in this following fashion. You have this, let's say, Gauss's law, where you have, in addition to the usual term, you have this new current term here, and you have in this expression here, you have these other, you have a new source term. Here you have these new current terms here, okay? One of the things that you can see in this is this theta parameter is coming in, but everywhere it comes in, it's coming in as derivatives. Derivatives in space or derivatives in time, right? So something has to change, either in space. If you had a real axion, if the axion was a real particle, you would have a fluctuating field in space and in time. We're going to think of these as static field, but something which can change in space. Where does it change? Well, it changes at the surface of the topological insulator. Inside the topological insulator, if I have inversion symmetry, in a symmetry protected phase, the axion angle is theta times an odd integer. And outside in the normal vacuum of everyday space, it's pi times an even integer, and we usually just take it to be equal to 0 in free space. Okay, so the only thing physically accessible are changes in theta. This idea that this theta parameter can only be defined, if you will, we can write it as theta is equal to 2 pi times n plus 1/2, and this can be defined as a bulk quantity modulo 2 pi. It turns out that I can change theta, because I only depend upon changes in theta. I can change theta through the whole universe by 2 pi, and nothing physically accessible changes. This is analogous to a gauge transformation. Now, a number of funny things I've said so far in the last few minutes. One of the funny things that I said was that the Hall response of the topological insulator is e squared over h times n plus 1/2, right? So n plus 1/2, the 1/2. That's a funny thing because we know again from Thales that the Hall response of a two-dimensional gapped insulator must be an integer times e squared over h. So where the heck does the 1/2 come from? The resolution of this is it turns out that the 1/2 actually comes from the bulk of the material. This didn't make much sense to me when I was first learning about it. You have a Hall response which is exhibited at the surface, but what it shows us is we really have no other description of these materials than the surface of a topological insulator is not a two-dimensional material, but it's a boundary of a three-dimensional solid, and that's going to be a very important point, okay? The other thing that I've said is that when we're regarding topological insulators as magnetoelectrics, is that I said that this magnetoelectric response, which is parameterized by this theta angle, was going to be in the topological insulator, was going to be an odd integer times pi if the material had inversion. Now, one of the things that any crystallographer can tell you about magnetoelectrics is that in order for something to be a magnetoelectric, it has to break both time reversal symmetry and inversion. Okay, so I've said a few things that seem to be a bit contradictory here. One, I've said that this theta parameter is going to be quantized if I have inversion, but yet I know in order to have a topological insulator, in order to have a magnetoelectric, I have to have inversion symmetry. Quantized magnetoelectric, I need to have inversion symmetry in the bulk. So it turns out that this one mysterious factor of 1/2 and this paradox between the magnetoelectric, which has inversion symmetry, these things are actually related to each other, okay? And in a very important and fundamental way. What I'm going to do here, instead of explaining it directly first, I'm going to give an analogy to a related system. Okay? The related system, and there are many analogies between 3D magnetoelectric effects and the example of polarization in 1D. So consider, for instance, this one-dimensional chain of ions. You can imagine them sodium and chlorine atoms laid in this particular fashion here. There's a problem with the usual, let's call it textbook definition of polarization. So we're told, if you open up a textbook and you want to know what the polarization is, we're told that the recipe is that you should go in and identify some microscopic dipole and then average that dipole over space and come up with this quantity of the polarization. Okay, right? That's what it says. And Griffiths and Jackson essentially says the same thing. The problem with that is that, oh, sorry, there was something else I wanted to say, but let's forget that. The problem with that is that I can choose this dipole, but I could just as easily choose this dipole here. And if I go and I take the first one and compare it to the second one, I get completely opposite values of the polarization. So in what sense is polarization a quantity which describes a macroscopic solid if it's up to me to choose the microscopic dipole and I could get completely different values of it? So this, if you will, ambiguity of polarization was a source of long-term discussion, particularly in the ab initio calculation community, as to what extent polarization was really an intrinsic quantity of solids. And was it something which really only depended on surface termination? This object here, you know, the finite size chain, it has a well-defined polarization that's associated with it, right? There's a plus charge there and a minus charge there. There's electric dipole which points in a particular fashion. But if I remove surfaces from it, I shouldn't have to define surfaces if I want to define a quantity in terms of a bulk polarization. And so what was eventually realized was that the quantity of polarization is actually a multi-valued quantity. We actually call it a lattice of values. And that the notion that, that we can choose the macroscopic dipole, the microscopic dipole, which then changes our definition of polarization, led us to the point that it was realized that there actually, in polarization, there's a polarization quantum, and that we cannot uniquely define a particular value for polarization for some system, but we can only define some lattice of values. And all of these lattice of values are related to each other by some polarization quantum. I can end up choosing a microscopic dipole like this, but I could imagine taking, for instance, and doing a transformation on the bulk of this material where I move, let's say, all the charges through each other. That is a transformation to this solid that leaves the bulk completely invariant, but flips the sign of the polarization quantum, right? So what we realize then as well is that not only is polarization a multi-valued quantity, but it has a particular quantization. If you look at the difference in the macroscopic polarization of this set of charges and this set of charges, it differs by exactly the fundamental electronic charge E, right? So it's not that I can pick any polarization I like in the system. I can pick a set of polarizations, and they're all separated from each other in this lattice of values by the polarization quantum in one dimension, which is just the fundamental electronic charge E. Okay? Now, one thing to note then is that this structure is, in terms of the bulk, is inversion symmetric. If you ask a conventional crystallographer and you would ask them, what's the polarization of inversion symmetric structure, they would tell you 0. But that structure does not have polarization 0. The polarization of the whole structure is not, yet the bulk is inversion symmetric, right? This guy here also doesn't have a net 0 polarization to the whole structure, but yet it's, of course, also inversion symmetric. And I go from here to here. Those are two different polarization values, and they're separated by the polarization quantum E. There's another lattice which is possible, which also has inversion symmetry. Okay, which one is that if I take these? Well, it's kind of a fictitious lattice, if you will, but I can imagine there's another lattice where I take the positive and negative charges and I just slide them on top of each other, right? So imagine sodium chlorine atoms, and now they're just sitting on top of each other. Doesn't exist in real life, but you know, as a thought experiment, it's fine, right? This structure in the bulk also has inversion symmetry, but it has a well-defined polarization as reference to some kind of reference state, just as the two different lattices I was talking about before in terms of positive and negative charges also had a well-defined polarization difference between them. Now, if I take this structure and I sandwich it between the original structure, and I go in ahead and I imagine these positive and negative charges are kind of smeared out over space a little bit, and I ask how much charge is in one particular place and another place, what I will find after I smear out the charge a little bit, that I have a half an electronic charge which is trapped at each of these interfaces. Half an electronic charge local in space. So I've gotten fractionalization of charge somehow. This should remind you of a number of different things. It should remind you of the 1/2 of the n plus 1/2 times e squared over h. Okay, there's 1/1/2. It should also remind you of the lectures from yesterday talking about fractionalization in the 1D topological insulator chain. There's a very related thing which is happening in that case there, where you have these local bonds that are forming electrons, but at the ends of the chain you have this kind of leftover bits of the original wave functions. Here you have a charged neutral bulk, but then you have at the ends you have these regions in space, there's 1/2 electronic charge which is trapped over here. And this arises, as you can be convinced by thinking about it for a little, or you can convince yourself, as arising from a bulk property of the material. Okay? So this notion of charge fractionalization that comes, if you will, from kind of neutrality in the bulk, the requirement of charge neutrality in the bulk, this comes up in a lot of different contexts. There's a related thing which you heard about in the 1D topological superconducting chain yesterday. It's a very similar thing in the one-dimensional Haldane chain. You get 1/2 spins at the end of a charge, as a spin 1 chain. Haldane also, of course, did that work and is here. Okay, and the point is that there's these ambiguities in local measures of polarization, and they resolve themselves. We can define polarization. The takeaway messages are twofold. One, that we can define polarization even in inversion symmetric structure. And two, if we have inversion symmetry, that tells us certain things about what the end charges have to be. They have to be 1/2, have to be an integer times 1/2 the electronic charge. This lends ourselves then to a cartoon of a topological insulator, a real space version of a topological insulator, and I think this kind of real space version is unappreciated. If we think of a conventional insulator, one particular representation of a conventional insulator, if you will, is overlapping layers of e squared over h Chern insulator and minus e squared over h Chern insulators, when these guys are kind of just sitting right on top of each other. This situation for just one of these slabs is exactly what happens in one of these transition metal dichalcogenides. So say the Moly sulfur 2 that I just talked about. There, one of the valleys, let's say the K valley, has e squared over h, and the other valley has minus e squared over h. They're on top of each other, giving you no net Hall conduction and a trivial material, but kind of these two overlapping Chern insulator systems. So you can also imagine in some contexts things like gallium arsenide or conventional insulators are exactly that. What I want you to imagine here is some kind of hybrid structure where I've overlapped these layers, but the real material itself is the purple in the middle where things overlap. A topological insulator in real space is exactly this. You can imagine, again, these e squared over h and minus e squared over h layers, but organized in a real space fashion that they're canceling in the bulk, but they're leaving on the surface 1/2 e squared over h. So this is a real space version of a topological insulator, and the analogy I want to make with 1D polarization is that this 1/2 e squared over h is exactly like the 1/2 that's sitting on the surface charge in the 1D polarization. And again, this comes back to this kind of correspondence between polarization in 1D and 3D magnetoelectric polarizability. Okay, let me, in the interest of time, let me skip that and talk a little bit. There's all these various different things one can say about the theta angle, and we can talk about that if you have questions. But I want to go on and tell you what we've actually done for experiments. These are time domain Terahertz experiments. You're all experts on this kind of stuff now because I've been talking about it for 2 days. This plot you've already seen of these laser pulses propagating around the table. They're interacting with these photoconductive switches and making these pulses of terahertz radiation. It's about a picosecond long. An inverse of a picosecond is a terahertz, right? And so it has all this Fourier content that we're interested in. The samples are super, super hard to make, but we're not going to talk about that. They're made up the road here at Rutgers. That is a plot that you've seen already, where I talked about the sum rule in the optical conductivity. So this is the real part of the conductance and the imaginary part of the conductance. this big peak here at 1.9 terahertz. That's the phonon, right, of the so-called alpha mode of the phonon and bismuth selenide. And what we're interested in is here at low frequencies, where there is this peak at zero. It's peaked at zero frequency, and it's about a terahertz wide. And this is this peak that is coming essentially entirely from the surface state transport. And again, remember, there's a real part and an imaginary part to it. And so this is a kind of a good starting point for learning about optical conductivity data, because there's a lot there. This is the slide I showed you yesterday, which was about the sum rule explicitly. And if you remember, we have sum rules in the optical conductivity which relate the area of various features to the density of the carriers that are responsible for that feature. And so what I did with this data, the red curve in here is the data that I just showed you, which was of a particular thickness of 64 unit cells. But then there is data of different thicknesses. And I went and I fit the area of the Drude curve, and I fit the area of the phonon. And the thing we found was that the area of the phonon scaled linearly with the thickness. This is the area versus the thickness. The phonon goes linearly with thickness, whereas the Drude was independent of thickness. And in this sense, I was able to identify the Drude as a surface state feature. Okay? This is all the physics of this thing when we're having it at zero magnetic field. The magnetoelectric effects are going to come out when we're going to apply a magnetic field to it. Let me show you one other aspect. I'm going to need, I think I have about 8 or 9 minutes left, right? And I'll need another few minutes beyond that to give you the full story. So one other thing that we worked on here, which I think is interesting and kind of will further convince you that the general phenomenology we have here is valid, is we looked at this class of materials. Bismuth selenide is the topological insulator, but indium selenide is a conventional insulator. And when you substitute indium onto the bismuth site there, you can form a solid solution. Bismuth is a big, heavy atom with lots of spin-orbit coupling. Indium, well, we don't usually think of indium as a light atom, but compared to bismuth, it's a light atom. And so when you substitute, oh my gosh, when you substitute indium into the bismuth selenide, you form a solid solution, and you can tune from the topological phase to the non-topological phase. Now, one of the things that you recall, and I showed you this plot of the bands crossing each other with the valence band and conduction band, and I compared it to kind of the conventional system like, let's say, gallium arsenide, or even, if you will, the cartoon, where the two roads had to cross from going from Hong Kong to mainland China. We know that we can't go from the topological side of the transition to the non-topological side without closing the band gap. So if I substitute indium into bismuth selenide, the only way to go from TI to non-TI is to close the band gap. And so what is plotted here on the left side is the absorption coefficient of the system as a function of the indium concentration, absorption coefficient with respect to light, here not in the terahertz range, but at 0.3 electron volts, so reasonably high energy. So, but what you can see is that we put indium into the system, there's a peak in the absorption, and that peak is at about 6%. So it's very, very sensitive to the indium substitution into the system. As we put indium into it, the band gap just comes screaming down and closes really, really, really quickly. And then, if you will, kind of passes through each other, and the gap opens back up as we come into the conventional insulator. So when we did these experiments here, we had already identified 6% as the point where the band gap closed. Now, we went then and we did terahertz experiments, and this is a plot of the real conductance versus frequency. And this is, again, this alpha mode peak. And one of the things that you can see is you put indium in, the phonon moves to higher frequency. Now that's expected because phonons depend upon 1 over the square root of the mass of some phonon coordinate. And so indium is lighter. And so as you substitute indium in, the phonon moves to higher frequency. Of course, what we're interested in is at low frequencies. And the red curve is the data that I've been showing you. So what happens is, as you substitute indium in, this curve gets broader. And that's expected, right? Indium, kind of in the semi-classical transport regime, indium is a scattering site where electron going along the surface bumps into indium impurity, and the resistance of the system should increase, or the scattering should increase. But you can see what happens is it gets kind of broader and broader and broader until we hit like this 5% level, where the curve is just completely broad, and then flunk, the whole thing goes away altogether. We can take that data with the real and the imaginary part at the same time. We can fit this Drude scattering rate, which is essentially this width of this feature. And for that particular set of samples, it does what I just told you it does. the scattering rate kind of comes up, starting from pure bismuth selenide, comes up, and somewhere between 4% and 5%, there's this very quick jump or crossover to some other behavior, and then it kind of continues and keeps on going. Now, when we saw this, when we initially saw this, I looked at it and thought, okay, great. We already know the transition happens at 6%, and as far as I was concerned, this 4.5% where the gap, this jump happened, this was exact agreement. We did more measurements. We realized that our measurements were good, the samples were really good, and this was always at slightly lower, this jump was always at slightly lower concentrations than we expected for the band gap to close. We thought about it for a while, and we finally realized that this is exactly what should happen, and it's a finite size effect. And what happens is the following, is that there are these surface states, and they have conduction. The surface states are surface states, but the wave functions have some evanescent depth into the depth of the film. And so the wave functions have some kind of exponential fall off. And one can show that the evanescent depth of the wave functions goes like 1 over the band gap of the material. Right? So as you go from bismuth selenide to the indium selenide, the band gap closes, the wave functions penetrate deeper and deeper into the bulk of the film. And at some point they start to overlap. Now, the surface states of the topological insulators have a property that we call spin momentum locking. If I consider a particular state K, it cannot backscatter directly into this state minus K because the spin is pointing the wrong direction. But as these wave functions start to overlap with each other, an electron going along in state K can scatter into the state minus K because it can scatter into the wave function on the other surface. So what we did is went ahead and did some measurements on many, many, many samples. Our collaborators at Rutgers were incredibly generous. So these are different samples. The data in red is the data I've just shown you. The other data is samples of different thicknesses. And what you can see is that this jump happens for different thicknesses. And as the samples get thicker and thicker and thicker, you approach the 6% level where we believe the band gap inversion transition happens. So what this is kind of like a direct, real version of finite size scaling. So the notion of finite size scaling is kind of a standard technique in looking at phase transitions where you kind of look at the effective size that the system sees as a correlation length diverges. This is real finite size scaling. So we've really looked at different size samples and seen how does the critical behavior crossover, and there's really some kind of change in length scale as you approach the critical point, and the system length scale eventually dominates the diverging length scales themselves. In the interest of time, let me just skip this, and I want to show you the final thing that we were interested in, and this is in particular on this quantized magnetoelectric effect. Now, what we've done in measuring the quantized magnetoelectric effect is we've developed a way of doing very, very accurate terahertz polarimetry. Okay? So it sounds rather prosaic, but it's quite important. We take linearly polarized light, we shine it through the sample. It goes through a few polarizers, if you will, first to kind of set the polarization state. It goes through a sample and can undergo, as it passes through the sample, can undergo a Faraday rotation. The Faraday rotation is the rotation of transmitted light through the sample. It can happen in magnetic material, and here it happens as a result of interaction with these magnetoelectric effects in the system. Okay? We developed a way of measuring this very accurately. We have a 2-inch polarizer which spins at a few thousand RPMs. What this technique allows us to do would be to go from the previous state of the art, which was about 1 degree in angular resolution, to something now of order about 10 milldegrees. So we can really measure tiny, tiny shifts in polarization. We use it for looking at explicitly magnetic materials. We're using it looking at cuprate superconductors. And here it's been used, I think, quite successfully in looking at topological insulators. Why it's sensitive, particularly sensitive, this is a story in itself. If you're interested in it, we can talk about it. Let me skip through that. So this here is a plot of the real part of the Faraday rotation as a function of frequency at different magnetic fields. It's a movie, and so I'm going to play the movie. And so what you see as I increase magnetic field, you go from, the movie's going to replay itself, this kind of threshold behavior which moves through the spectral range and eventually out to high frequencies. Okay, that is actually the classical cyclotron resonance, moving out to higher and higher energies, and eventually the classical cyclotron resonance is out at high energies out here, okay? What you see, though, left behind at low frequencies is that the data falls right on this dashed line. This dashed line is set by, this is the prediction from this topological magnetoelectric effect, 2 alpha, where alpha is the fine structure constant, times some combination of integers, where you have the 2 sets of the 1/2 in here, divided by 1 plus n, where n is the index or refraction of the substrate. Okay, so this here is for a number of different samples, which have n in all of these cases is the number of filled Landau levels on the surface, and in samples with different densities, one can see always the limit of low frequency. You're right on these lines, quantized, or on the predictions for the quantized lines here. One of the things that we can do in these experiments, and as I told you from the early lectures, is from semi-classical transport, the area of this Drude peak is a quantification of the number of carriers in the system. So we apply a magnetic field to break time reversal symmetry on the surface. We know the density of carriers because we know the areas of these Drude peaks, so we know what the filling factors are on the surface. So this is a plot of, if you will, this quantization index, this combination of integers, as a function of the filling factor, which we can measure directly. And what you can see is that you get these series of plateaus here. And in all cases, they lie on this blue dashed line, which is offset from the diagonal line by a factor of 1, or by a piece which is 1. Right? So the quantization index always shows this offset, means that since we have 2 surfaces, each of the surfaces is showing a contribution which is offset by 1/2, and as we've discussed, this 1/2 is really a signature of the bulk topological magnetoelectric effect. You can ask yourself, I need like another 2 or 3 minutes. So you can ask yourself, is this just the normal integer quantum Hall effect in the surfaces? And the answer is no. For one thing, the answer is no. I wanted to be unambiguous. The answer is no. For one thing, the answer is no because we have this offset. And this offset of 1 from the 2 surfaces, each surface is contributing 1/2. So each surface is giving a contribution, which is 1/2 times e squared over h. And as we've discussed, you can't get 1/2 e squared over h from a 2-dimensional material. It has to be the boundary of a 3-dimensional material. But the other reason why it's no is that one might think when you're doing such an experiment that you take, let's say, the surface of a topological insulator, put it in magnetic field, and then maybe get some edge states in this particular fashion, as you would, let's say, if it was a 2D electron gas. But topological insulators are not that, they're really this. And so if I take a topological insulator and I put it in magnetic field, I may get some kind of quantum Hall effect in the top and bottom surfaces. But the side surfaces, these see a sideways of magnetic field, there's no gapping, there's no quantum Hall effect which happens at the surface. And if I come in and let's say imagine I go and I I try to do a transport experiment on a slab of system like this. I'd run current through it and I attach, let's say, some electrodes on the 2 sides to measure the Hall effect, the Hall voltage that occurs. That Hall voltage will get shorted out by these side surfaces, which are non-chiral. In the quantum Hall effect, charges are only going around the sample in one direction, so the shorting out can't happen. And in fact, this is exactly what we see in DC quantum Hall effects on the same samples. So when we take one of our samples and we put it in a very large magnetic field, this is the Hall resistance here as a function of magnetic field. At 30 Tesla, it shows a quantum Hall effect of h over e squared. But the region where we are seeing our quantized magnetoelectric effect is down here. So in a regime where the DC transport is completely semi-classical, this AC effect, where we're really just looking at the regions of the surface which are kind of gapped because they're exposed to magnetic field, these show quantized transport. I'm out of time. The final thing I just wanted to say was that, although we can see this quantized Faraday angle, it's not quite, in addition to the complexity of doing the experiment, it's not quite as nice measurement as the quantum Hall style experiments where really just the thing you measure directly is a universal constant of nature, because one of the things that factors into those dashed lines and those plots for the Faraday rotation, if you will, given by this expression, is the index or refraction of the sapphire substrate that it's sitting on. What we've been able to do, though, is use the time structure of the terahertz pulse itself, where we use the sapphire that the sample is sitting on as an optical resonator. The terahertz pulse passes through the sample, undergoes a Faraday rotation. Some of the light goes on and we measure. but some of the light reflects inside the sapphire, undergoes another interaction with the film, and undergoes a Kerr rotation. And so you get a series of peaks, each of which encodes a different history of interaction of the pulse of the film, and each of these, if you will, is related to kind of intrinsic sample properties in a different fashion. And you can see the Kerr rotation, the index of refraction appears in a different way than it does in the expression for the Faraday rotation. So we can actually measure the Kerr rotation at the same time, and what this allows us to do is give you a purely solid state measure of the fine structure constant. So the accepted value for the fine structure constant is 1/137.04, and our, let's say, best measure of it from our samples is 1/137.9. So the error is in the fourth decimal point. It's really the first measure of the quantum Hall effect, sorry, not the quantum Hall effect, of the fine structure constant from a purely solid state measure based on a topological invariant in this fashion. It really comes from the fact that this quantized magnetoelectric effect is present in these topological insulators, and is really the response function which directly encodes the topological properties. Again, it's a very rare one. I'm basically done, but I want to come back to what my point was in the beginning of this, was that we're interested in these various phase effects, these Berry curvature, Berry connection. They manifest themselves as topological properties of these systems, but there are very, very few systems that present themselves with a crisp, clear measure of this physics when it's quantized. The quantum Hall effect is one, and the second one is the quantized magnetoelectric effect in 3D topological insulators, which is here. Other than that, I would say right now this is a huge area of possibilities for experimentalists as well as theorists of thinking about what we can actually measure, which is quantized and universal in the same way that quantum Hall effect or the 3D magnetoelectric effect is. So that's all I had to say. I'm happy to take questions with any other extra time, and thank you for your attention.
Okay, we'll be back here in 10 minutes. If you have any questions, feel free to ask.
Okay, thank you.
2004